Today's lecture is about balls, bins, and hashing. But first, let's start with a funny paradox called the birthday paradox. So the birthday paradox is typically concerned with a classroom full of students. There's some number of students. The question is, what's the probability that there will be a pair of students with the same birthday? Another perspective on this birthday paradox is how large the class be before you expect to see a shared birthday. And at first sight, you might think that you'll need quite a few people in the class, say about say at least something like 100 students in the class, because there are 365 days. But quite surprisingly, somewhat at least, you can expect to see a shared birthday around the 23 students mark. So when you get 23 students in the class, you're likely to see a shared birthday. Why is this? So let's think a little bit about that, and in course of doing that, we will develop an understanding of the balls and bins model, which will be helpful for us to visualize what's happening in the birthday paradox. Okay, so without further ado, let's talk about the birthday paradox. So let us begin with the assumption that there are n days in a year. So this is more general than the 365 days that we on Earth are used to. But let's keep things general in order to help us understand how the flavor of balls and bins will work. And now let us assume also that a student is equally likely to have been born on any one of those n days. Okay, so we're going to work with these assumptions. So the question that we are interested in is how large should the class size be, and let's denote the class size by C. How large should C be such that the probability that there exists a pair of students in that class of C students who share a birthday, and that probability, we want that probability to be at least a half. So let's see how this birthday paradox question can be analyzed using the balls and bins model. In this model, we have n bins, so we identify these bins from 0 to n minus 1, and we have m balls. And we assume that each of these balls is sequentially thrown into one of the bins, and the choice of bins is equally likely to be any one of the n bins, and moreover the balls are thrown into bins chosen independently of each other. So let us now try to rephrase the birthday paradox in the language of balls and bins. We are interested in the smallest number of balls that need to be thrown before the probability of a certain event becomes more than a half. And what is the event? It's the event that 2 balls out of those C balls share the same bin. And this is exactly the birthday paradox, except we've now phrased it in the context of balls and bins. So let's see how this question can be analyzed. On purpose, we're going to be a little bit sloppy with our analysis, mainly because we want to ensure that the intuition behind this paradox is brought out in a clear manner. So the emphasis on the intuition, but you will notice if you look into the book, there are many different ways in which this particular scenario can be analyzed. In fact, there are better ways, more cleaner ways to analyze it, but we are going to choose this particular technique to analyze it only because it brings out the essence of the idea, the clear intuition behind it in the best possible way. So we have n bins. We're going to throw balls in 2 phases. In the first phase, we're just going to throw square root of n balls, and there may be collisions, so there may be cases where 2 balls fall into the same bin. but really we are concerned about getting a good lower bound on the probability that a pair of balls will fall into the same bin. So in a in a pessimistic way, we're going to assume that in the first phase there are no collisions, that these balls all fall into different bins. In phase 2, we will place the second square root of n balls, but now we'll have to be a bit more careful. So our entire focus is going to be on phase 2, and let's ask the question, what is the probability that a specific ball in phase 2 falls into a non-empty bin? Well, this probability is more than the probability that the ball falls into a bin with a phase 1 ball in it. Why? Because there are going to be fewer bins with phase 1 balls than the total number of balls, because this could be any ball in phase 2. So the phase 2 could have brought in a few extra balls before our specific ball comes into the picture, right? So we're going to ignore all of those balls. We're just going to bound this probability by the probability that the specific ball falls into a bin with a phase 1 ball in it. And this we know is equal to 1 over square root of n, which implies that the probability that the ball falls into an empty bin is at most 1 minus 1 over square root of n. Thus, the probability that all the phase 2 balls fall in empty bins can be upper bounded by 1 minus 1 over square root of n, the whole raised to the square root of n. And of course, this is at most e to the minus square root of n by square root of n, and that's of course 1 over e, which is certainly less than a half. So clearly, at most 2 times square root of n balls are required before the probability that we see a shared bin for a pair of those balls exceeds a half. Of course, the birthday paradox is a very well studied notion, and as I mentioned, there are several tighter analyses for it, but this balls and bins way of looking at the birthday paradox is particularly insightful. It's very easy to see how the phase 2 balls operate in the presence of the phase 1 balls. We're making a few pessimistic assumptions that kind of make it clear as to how the balls behave, the phase 2 balls behave, and the square root of n, the asymptotic limit at least, kind of comes out very cleanly. And also, as you might have noticed, the balls into bins model is pretty elementary, but it's actually quite powerful in the number of ways in which it can be applied. In this case, we've seen how the birthday paradox can be viewed as a balls and bins model, but of course there are many other interesting problems, especially algorithmic problems, that we are going to be able to view as instances of the balls and bins model. For example, we can view the coupon collectors problem as a variant of balls and bins. Hashing, which we are going to study now, will be viewed as an instance of balls and bins. So we're going to be able to use it in a variety of ways. So it really helps for us to have a good understanding of how to analyze balls and bins questions.